We'll talk about metaprogramming, and we have a lot to see in examples, so straight to the point. Metaprogramming, while programming is usually taking data and producing some data, metaprogramming takes programs as input and produce programs as output. This is the main difference. Of course, if program is represented in memory, it's also data, but we emphasize this point of view where we transform one program to another program. And why we may need to use metaprogramming, usual use cases is to avoid overhead of abstractions, automatic code optimizations, generate boilerplate, develop DSLs, tweak syntax of the language. In particular, if we're talking about Scala language, we can use Scala Macros to this kind of metaprogramming. In Scalan, we mostly focus on first three parts. We are not focusing on syntax and concrete syntax in particular. Typed metaprogramming is when we want to have some help from compiler in terms of if it is statically typed language, we can use compiler type checking to have some to verify some properties of our program. And typed metaprogram takes typed program and produces typed program. So why metaprogramming is hard is because we usually deal with very complex data structure which represent the program. So this is abstract syntax of some language which is defined by recursion on types. So you can see this recursion on types. And also recursion of terms and different kind of constructors which we can use, and some multitude of primitives and pattern matching and so on. And this formal definition of language should be respected when we do some metaprogramming, and all operations and all metaprogramming essentially become recursive operations. And the hard part is to manipulate such data structures in some semantically correct way. So how Scalan as a framework can help with this complexity? So the first thing is that Scalan provides unified intermediate representation, which is based on graphs, directly acyclic graphs in particular. It is immutable and also allows to use higher order abstract syntax technique, and also has some configurable visualization subsystem which allows to visualize these graphs. When you develop metaprogram, it's important to have this visualization. And also, in order to build metaprograms, we need to have some composition tools, and this is composable and generic representation is another component of Scalan. In particular, we have unified representation of functions. We have virtualized user-defined types, which we will discuss later. We have domain-specific isomorphism is a unique Scalan tool which allows you to identify in your particular domain what kind of isomorphism exists between data structures. And also domain-specific conversions, because sometimes you need to convert one data structure into another, and you can generate converters in Scalan. And what's shown here is that we regard user-defined types as first-class objects in the framework. It means that framework not just come with some predefined types. You can, as in Scala, you can define using Scala your own types. For example, collection is a library which is written in Scalan, and vector is another library which is, and matrix is a linear algebra library which uses collection, and matrix also use vectors in definition. So this definition of types is first-class citizens in the framework. And also, the third, the most important component is composable and generic meta operators, which can be, which define it and implement it in Scalan and can be reused across different domains for your particular domain where you may use the framework. You can use these meta operators to compose your meta program. So before we go some examples, we need to discuss some basic machinery which is defined inside the framework. So first is code virtualization. This idea comes from Scala virtualized, but in Scalan it's implemented completely in different way, and we don't use a special compiler. So Scalan is based on recent Scala compiler, standard compiler. And the idea is also called lifted embedding, which is known from LMS and also from Slick lifted embedding. We transform the original program in some systematic and automatic way. We lift types into special type rep, which stands for representation, and this allows to abstract from the representation how we want to represent these types. And we also perform some systematic replacement. For example, instantiation of objects we replace with factory method calls, and we can also replace lambdas with special function which allows to reify this lambda. So this systematic transformation makes the code somehow abstract. This code does not have any particular representation of the values. And this can be done automatically by Scala plugin, and this can be done manually. So if we look at the broader context, this code virtualization, if it is implemented as a Scala plugin, can actually be placed after the typer in the compilation pipeline of Scala compiler. Or it can be implemented, this code can be written manually without much of the boilerplate. So this rep types is the only thing, and this additional elements, which is implicit values, is another thing which you need to take care of while writing programs, and everything else happens in the framework. So another idea and the notion which we will discuss today is standard evaluation. So when we're talking about evaluation, we usually have, for example, consider this expression. We have radix in this expression. Radix is something which we want to evaluate in the expression. And this evaluation, according to Scala semantics, is applicative order. So this is the innermost radix in this expression. And as a first step, we evaluate it, and now we get not expression, we get data. And then the next radix takes this data, we perform next operation. Now we have array in memory. This is a rough description just to get the idea what's going on. We take an expression, and this expression during evaluation transforms into value, and then we get the value. So this is the result of this expression when this expression is evaluated in standard way. So staged evaluation, on the other hand, is the technique when we give completely different interpretation for the same expression and evaluate this expression not for execution of data and to get data as a result, but to get some intermediate representation as a result. For example, we have the same radix, but now when we do first step, we produce the node of the graph. And this node has two components. One component is symbol, which is assigned to this node, and this is like an address of this node. And also the definition, which has this, in this particular case, we have constant definition. And we get this symbol as a result. So instead of data, where on standard evaluation we had data, now we have symbols of the graph at the same place. And now we have second radix. We perform another step of evaluation. Now we create a new object, and then we transform method call. The result of the whole process is some intermediate representation in the form of graph, where different nodes are connected by the symbol which are used as the arguments. So, of course, this would be useless if we could not generate some code which we can actually execute from this graph. This staged evaluation is supposed to be used together with some code generation. And it can be understood as a self-reproducing process. So this program, when staged evaluated, produces some intermediate representation for which we have code generation, which can, in particular, reproduce the original semantic of the code. But because we have this intermediate representation, what we can notice here is that, for example, this program is not very efficient. We first we create array, and then we get only size of this array. So we can define this rule for any n. If we construct new array n and then take size, then we can just rewrite this graph to use n. So as a result, we can get this code, which is much faster. Of course, this is a very simple example, but the good thing is that we can define in Scalan many different rules using both Scala pattern matching machinery, and we can also have DSL developed in Scalan itself, so it's like reusing Scalan for its own purposes to develop rules DSL where you can define declaratively such kind of rules. And then every time the new nodes is added to the graph, the whole system of rules is checked, and the effect is like saying when you add some rule to the system, the effect is like you saying, please, if you see this pattern graph on the left, replace it with some graph on the right. And graph on the right is constructed by using the same staged evaluation approach. So it's completely a reuse of the idea of self-producing and the staged constructing graphs using staged evaluation process. Another important notion is how because if we want to represent Scala programs in some intermediate representation, we need some way to represent functions. And in functional programming, function is the first class citizen and the main object which we want to compose. So how we represent lambdas and functions. We have this interface which stands for AST graph, and lambda is one of the possible implementation, what concrete implementation of this interface. And also there are existing different nodes, and lambda is a node here. There are different nodes like sunks and branches of ifs, and also the kernels which we can generate from graphs which can be executed, also different kinds of instances of this AST graph. And the picture on the slide show how this graph is constructed. It's constructed as intersection of different sets. So the first set is so-called up nodes. Up nodes when we take some result of the function and we build the set of nodes from which this result depends. So we take this universe of different nodes in the graph and we build the set of nodes. Then we build another set which is down nodes when we have these bound variables of lambda, we go down the graph and build all the nodes, create a set of nodes which depend from these lambda arguments. In this particular case, we see this node depends on this, and this node depends on this, then it means also depends from the arguments, and so on. But, for example, this node does not depend on these arguments, but they are used inside the nodes which are depend. So the scope here is lambda body. So the body of the function and lambda is lazily computed by intersection of these two sets. And all the external references become free variables. So it's maybe a question, why such complex construction of lambda, and is it possible to do it in different ways? So we try different representations actually, and this is the fixed point where we converged somehow. So it allows to make, because we're working with graph, we don't know, when we transform this graph, we actually don't know the final structure of this graph, and syntactic scope, we cannot have strict syntactic scope. So these scopes became dynamic. And if we look at the whole picture of what we just discussed, so code virtualization has some semantic meaning. So if we have our original program, and we can execute this program, it's a Scala program, we can execute this program, and if we give data to the program, we get result back. And this is our original semantic function of the program. Then we perform code virtualization of the program, and we produce P virtualized, which have standard evaluation, which if we give the same data, we have the same result. And if we perform staged evaluation of this program, we produce some intermediate representation, which is also equivalent to all previous functions with respect to compilation and run. So this is the main concepts to discuss. And now we have an example. So everything we have in Scalan, we should define in some kind of in cakes. So this is a cake which we should inherit in our example. And we also call it abstract context because in this code is virtualized. And the fact that it is virtualized, it means it's because this rep constructor is not defined in this context. So this is just abstract type. So how to interpret this first statement? We assign 10 to something which is abstract, and the compiler agree with this. So in fact, we have implicit conversion here, which takes any value of type A, and with some additional descriptor element here stands for type description. It's similar to manifest or type text in Scala. In Scalan, we use two kinds of descriptors. One is elements, which characterizes types, and another is containers, which characterize type constructors. This is completely different notion, so this is different kind of interfaces. And this implicit conversion automatically produces this rep value. If we look at this definition, we see that this is just a method which calls another method, and this can be overridden. So in principle, in your DSL, you can define your own way how to embed values into this representation type. Another example here is when we have this abstract value x, we want to plus 1 this and get another value. If we look at the type, we see also this is inferred type int. So both compiler and the environment helps us to check the type. So this is statically typed program. Even so, it's abstract. So we remember this. And this plus is actually extension method, which is defined in the framework for any value, any type t, provided we have also numeric evidence that this is, we have instance of numeric. And here we can define function. This function takes some abstract value and then decompose this pair. We get x of type int and y of type int, and we can plus them. And then these constructions allows us to take Scala function, because plus is actually a Scala function, which from rep to rep. We can take this Scala function and produce rep value. So we like lift this function into some abstract value. And this example just show we call this function and print something in console. So if we look to run this example, so it works as expected. Even so, this is it was abstract code. Why it works is because we actually call this method run from the cake, which is inherited from standard evaluation context. This is like we have three cakes in the framework. One cake is for abstract context, and you can build different DSL and assemble into one cake. And this will be your abstract context. And then you have also standard evaluation context and staged evaluation context. And everything you write in abstract terms have two interpretations simultaneously in standard evaluation context and staged evaluation context. For example, if we run staged context, we see we have the same code, but now it runs with symbols. So it outputs not values, it outputs the names of the symbols. And if we go back to this and hit a breakpoint here, so we can run in debug mode. Because this is Scala and standard IDE, and we use standard toolchain, we can use all the benefits of standard toolchain and actually debug staged evaluation. It takes some time to start in IntelliJ. Okay, so this is debugging session. So now what we see here is that this code has been run, this function was invoked, and then we get the value of z, and we show this z show, which produce some graph we show on the in separate window. We can do this for any value. For example, we can take x. Yeah, so x is just const 10, and we can y. So y is different graph. So it's some visualization while you debugging your process of staging graph. You can visualize all the intermediate states, and you're actually sitting inside sitting inside stack. So you can see where in your program you are. So this is like a stack. Okay. So, and observing graphs is not the main goal, of course. So we can generate kernels. So once you have your definition of some function, and then you constructed your graph, then you can generate different kind of kernels. So this is example, we show how to do this. So first, we have this staged evaluation context. And then we define open some kernel store, providing some location where the kernel should be saved, or for example, on file system. And then we can use this function from our context. So this context, if we trace back, this context is our example X, which is our example here. So we trace back to this point. From our context, we take plus fun function. You see, we can navigate easily, because this is just standard Scala. And we can ask, please generate kernel, which is Scala kernel, from this function. And we can take the data and get some result. And this is actually the same data which we used for example, this is standard context, which allows to do just standard evaluation. And we compare these results. We can also generate C++ kernel, and for this reason we also use this GNI extractor trait, which we mix in to have some GNI transferring of data from JVM to C++. So if we run this program, okay, what it actually do, it's generates behind the scene, also generating Scala kernels took some time, generating C++ kernel. And then all the tests pass, and the test actually shows that the Scala result is equivalent to standard evaluation, and the C result is also equivalent to standard evaluation. So we get the same result in both cases. Okay, so this is demo 1. We also have the concept of generic meta operators. And the first thing to consider is isomorphism. So isomorphism is an interface which has two components. One is a function to, another is function from. And these two functions are mutually inverse. So if we compose them, we get identity. And here is an example which show the isomorphism between nested tuples and some flat structure. And these two functions, to and from. So in Scalan, if we compose these two functions, we take literally identity functions, so they collapse. It means when we perform staged evaluation of composition to and from, it collapses and we get identity function. And this happens automatically by rewriting rules, which does not allow you to grow the graph like this, because this is isomorphism. So this is isomorphism. Another, I forgot to say, you can actually build different kind of isomorphism automatically. You have a type, and there is some generic functions, combinators, which allows you to first compose isomorphisms and also build different isomorphisms. For example, this example shows the flattening isomorphism. This is generic meta operator, which allows to build these isomorphisms for any given nested tuple type, which is automatically flatten it into some structure. Converters. This is another meta operator. So suppose you have matrix interface, and you define it in Scalan matrix interface. And then you implemented your own implementation of sparse matrix implementation and dense matrix implementation. In these implementations, you use different representations of data. And if you follow some reasonable rules, you can automatically generate conversion between these two representations. And this is, if you think about this is not very trivial operation, how to transform this one data structure into another data structure, because this is actually domain-specific knowledge that these two data structures can be convertible. And in Scalan, you can define and design your data structures in such a way that they will be convertible to each one another. And this generic meta operator get converter, it's optional. Optionally get converter. For some data structures, it's produce none, but in some cases, produce conversion which you can compose with with different functions. And the third is called isomorphic specialization. And what it actually means is that suppose you have a function from some type A, for example, matrix, and some type B, vector, for example, and you have isomorphism from type A to A prime and from B to B prime. Then you can automatically generate function f prime, which equivalent, which makes this diagram commutative. So if you had, for example, function f from nested tuples to nested tuples, and you have an isomorphism which flattens these tuples, and it also flattens the result, then you can automatically get the function which works from flat structures to flat structures without tuples involved. And of course, canonical implementation will be just to compose this function. So we compose this, then we perform f, and then we perform another part of the isomorphism. And the nice property is that actually f prime is a result of staged evaluation exactly this formal composition. So if we perform standard evaluation of this composition, we go in this way. But because staged evaluation, doing the same kind of thing, and doing rewriting during this process, we actually get some specialized version of f with respect to this particular representation. So this quite generic method which works in many different scenarios. And this is also available from framework as a meta operator, which you can use in your particular domain. So I am showing on the matrices, but this is just a very simple, well understood domain for everybody. So the second demonstration is about matrices. So we have this example, define it in abstract context. This, if we can check it, rep is abstract. So we define matrix vector multiplication using some library of linear algebra. So this matrix is part of the package linear algebra, and this is defined in Scalan using Scalan framework itself. So this is a library written in Scalan. And the vector is the same. So we decompose input. Then we construct dense vector, take rows from matrix, and apply dot product for each combination. So because this is abstract arguments matrix vector, we need somehow call this function. How to call it? We need to instantiate matrices. How we instantiate? We build another function, for example, from nested collection. So using this nested collection and collection. So the first argument stands for matrix, and this stands for vector. And then we create dense matrix, dense vector, and then call our abstract function. But again, collection, if we look at the collection, it's also abstract type defined in Scalan library. So we still have abstract function, we cannot execute it. So we define another function which takes arrays and which also produces array. And we build particular implementation of collection, jagged collection. And this collection is from this nested array structure, we build jagged collection. And this collection is just collection backed by the array. And we call this function. And then we get values back. So here we have some test data, and again we have two cakes, which for standard evaluation and staged evaluation. So this example, we will try to run it. Okay, so here we have standard evaluation. We run it on our test data. Very small matrix and vector. So now this code is executed in standard evaluation. So all the rep types is just types. Means rep of int is just int. And in this case, we get some values and we get some result. Staged evaluation, on the other hand, because in staged evaluation we constructing some graph, we can generate kernels out of it. And if we run staged evaluation, it's a little bit longer process. Because we also do some benchmarking here. So it's generating Scala kernel. It took about 3 seconds, so 3 seconds for C++ kernel. We generated some example matrix random and also vector. And we calculated expected result using just regular Scala codes, using collection library. And so this took about 5 seconds. Now we are calculating standard evaluation. Because standard evaluation involves abstractions like matrix, vector, collection, they add additional overhead. And here we see that overhead is 3 times. So it's around 3 times. But then we take the graph and produced the kernel, which doesn't have all these abstractions. And now we have around 100 milliseconds in both cases. And here we also see that our C++ implementation maybe not the best way. Maybe Scala native would be much better choice for such kind of native code generation because it works not very much faster than Scala. Okay, so if we look, what's going on here is so this is how we calculated expected result. So this is just Scala code which uses arrays and reduce and array operations. And this took 5 seconds. Standard evaluation was involving abstractions which took longer. So, but if we go back here put a breakpoint. So what I want to show is how this graph, which is used to construct the kernels, this DMDV, is actually looks like. So if we try to show DMDV. Sure. Sorry. Okay, yeah, so here's the graph. Notice this graph doesn't have any abstractions. Even so, we actually executed some composition of functions we called original abstract function for matrix vertex multiplication. Then we wrapped it into collections, and then we wrapped it into array. And our stage evaluation was actually going through all these abstraction creations and eliminations. This graph doesn't have this abstraction, and this is what is the effect of isomorphic specialization. All the abstractions that you build is guaranteed to be eliminated during staged evaluation process, provided some requirements. If you wrap something into abstraction, you need to get a value back from this. So this is a property of isomorphic specialization. And how it works here, it works in combination with some domain-specific compiler, because it would be very hard for any particular domain which you can develop to develop optimizing compiler which take care of all the domain-specific properties. It's much easier to have this kind of guarantee of elimination of your abstraction into some base language, for example, array language, and then have compact optimizer for array language. For our prototype, we use LMS, and because LMS mostly has fusion of array operations. And if we look at the code which is created for this particular example, let me check. So it's here. So it builds all the kernel in some structure which we can actually observe. So this code has expected structure of matrix vector multiplication. So here we construct our result, buffer, and then we fill this result here. So we can use like this. So here we fill this result, and here we have multiplication, fuse it with summation. So this is just to illustrate that we combine here specialization from domains to some basic language, and then using specialized compiler for some particular limited language, like array language, for example, we can produce kernels. And we can produce kernels into different runtimes. And all these components is part of the framework which you can extend, adapt to your particular domain. So Scalan provides this kind of infrastructure which is centered around this specialization capability. So another point to discuss is we call it converters for free, because once you define data structures in Scalan, you in many cases have ability to convert from one data structure to another. Okay. So I also have demonstration. I don't have time to show. It is available on in GitHub. So this demo example will show how to compose. But the idea is this: we can call get converter like this. So we can have sparse matrix vector and as one type, and dense matrix vector pair as another type, and we can automatically generate converter between this input and this output. And we can compose this converter with matrix vector multiplication, which is abstract, but now we compose sparse matrix on the input and the abstract matrix vector multiplication. And the result is that we get the kernel which completely fuses conversion into the process of matrix multiplication. Okay, so this is a summary of meta operators. We also have some framework for rewriting rules. And we also, in Scalan, we have a multi-stage compilation pipeline where you can get initial graph, then you pass through different stages. At each stage, you can define your own domain-specific transformations. And then you can output different kernels for which you have a compiler. And we support C++, Scala, and Lua language. And we can execute these kernels. So this is the references for, if you got interested, we have a description of all that I said in some blog post. It's called Scalan metaprogramming idioms. We also have everything on GitHub. You can ask questions on Google Group and follow us on Twitter. And also Scalan publication, we have academic papers for this work, which if you are interested in the research component of this, you can check out this. And also, you can watch last year Amsterdam talk at Scala Days about integration of this into Scala compiler. So that's all. Thank you. Do we have questions? Do we have time for questions? Yeah. Yes, please.
So in LMS, you have the ability to have many different stages with many different abstraction levels, and then you have lowerings in between. Can you do the same thing in
yes,
Scalan?
Yes. So lowerings is one of the possible rewriting rules. So you can decompose high-level primitives into some combination of low-level primitives, and this is what lowering means. Yeah. Yes, please.
Okay. When you did these benchmarks to see the performance of the different executions, did you then take the effect of the JVM just-in-time compiler into consideration?
The performance difference, actually we take in consideration JIT compilation because we run it normally in Java. So it's just JVM is not able to, in this run at least, not able to deal with these abstractions because JVM takes method at a time, and here you need to pass through different abstractions.
I mean, they say that when you measure performance of stuff running on the JVM, you should usually sort of run the same code multiple times before you measure to warm up the JIT and stuff like that.
Yeah, but here the main bottleneck and the main problem of execution speed is not that the fact that JIT is not involved here very much, but the fact that we implemented our algorithm in declarative copying way. So every time we produce new data structure, and this is mostly memory bound operation now. So this is the main, and actually when producing loop and performing loop fusion, we actually generate imperative code from functional code. This is another aspect of this, and this is what LMS actually can do.
Okay, if I'm writing a library that in which I want to take some code written by the user of my library and to apply some transformations to it. For example, object relational mapper that takes some case class and I want to map it to some data structures in the database.
Right.
Can I do this with Scalan, and how much how intrusive would that be for the user code? Because I don't want actually to put any additional work on the user.
Yeah, this is a good question. So SQL domain in particular is very attractive domain for this specialization, because you can only not eliminate case classes, but you can actually change the representation of tables. It means if you have a query which you formulated using abstract table data type, and then you compose your query using tables, then you can give column-based or row-based table as particular representation. And you can automatically generate kernel which works with this particular representation.
Would the user have to then use all these reps and provide the implicits for generating these representations for Scalan, or could maybe the user just use pure Scala for that without any?
You need to use Scalan for this. Of course, because the specialization which you would like to do is actually implemented in this core. But it depends on, so if you want to do this at runtime, you need to somehow host Scalan at runtime. Yeah. But if you're interested in offline kernel generation, then you don't need to have Scalan in production. And this, for you, this is a tool which allows you to prepare the kernel.
And one more question about implicits. Standard Scala Macros have the ability to look up implicits at the time when the macro is expanded. Can I do this also with Scalan? So that from the representation, can I actively ask the compiler somehow to look up the implicits for some type?
Yes, we try to do this as plugin for compiler. So this implicits is machinery to allow this virtualized code to be encoded in Scala. So this is like a little bit of boilerplate. So, but because this is systematic program transformation, we actually implemented, at least in prototype, it's possible to do as a phase in Scala compiler and automatically lift all the original code into this abstract representation and into virtualized form.
Okay, thank you.
Could you quickly show us an example of the syntax for the rewriting rules? How do you write a rewriting rule? And how can you make them quite generic? Say you want a rule for any type of collection, for example.
Yeah. So if we want to have some generic rule, currently we have to use Scala pattern matching. So this is example of fusion of two maps. So we have array then we map this using one function, and then we result map again using another function. And so provided it has single usage in the graph, so we have only single chain of usage, we can fuse this combination. And this is example of the rule, how it can be defined. So we override, because we are in the cake, and we have many slices in the cake. Each slice have some override of this rewrite def method. And they are it's a stackable pattern, stackable override. And for our particular case, we define the pattern. If it is array map, and we have some argument here and some function, and here we also introduce type variables for our type, because this is where static typing become reasonable typing. So it's still checked something. So this code here is actually statically typed code, but it's statically typed provided we declare these types. And somehow we document this pattern using this type, because we take care if this array has elements of type A, then we should also use A here and there. So we define this pattern by using this pattern matching of Scala. We can, and of course this is just a Scala program which takes, and this def is requesting from arguments actual definition, which we check later match again. If it is array map, then we get these two functions f and g, and then we perform just staged evaluation, because this is abstract code. Here we have everything lifted into types. So this is just staged evaluation of right-hand side. What we want to replace original pattern, we replace it into this pattern. And here, these two functions inline itself into this lambda. And we get what we want.
Thank you.
That's all. So thank you very much.